wanted to mention, hey, Guillermo, good to see you. Thanks for hopping in. Other thing that I wanted to remind everybody about is that we have our midterm still going on. So some people have turned it in already, which is totally great. If you haven't yet, that is also 100% okay. It is not due until end of the day tomorrow. Where are we at? Week 4. Here we go. So you still have after class the rest of the night tonight and all day tomorrow to work on your midterm. Please get it turned in by the end of the day tomorrow. It is a relatively large chunk of your grade. And so make sure you take your time on it, read through the questions. You can reach out to me if you get stuck on something. I might not be able to help you figure out what the answer is, but I can help you figure out what the question is asking and what kind of answer that I'm looking for on that question. So still have plenty of time to work on the midterm. It's not due until just before midnight tomorrow night, Friday night. But do make sure that you don't forget about it and you get it turned in. So that's being said, let's go ahead and jump into our notes for today. So today we're going to be talking about bonds. Not like the financial kind of bond. Not like the 90s kind of bond. And not like the 2000s kind of bond either. Instead, we're going to be talking about chemical bonds. So these are the ways that atoms become stuck together. So like on Tuesday, I was talking about compounds and how compounds like water, H2O, and carbon dioxide, CO2, are different atoms that are stuck together. They're fused with each other. Chemical bonds are the way that they do that. And so today we'll talk about how chemical bonds are made and what the two major different types of chemical bonds are. So just as kind of a refresher of all the stuff we've been talking about so far, we're still dealing with atoms, the smallest unit of matter that exists. And atoms are made up of 3 different particles. There's this positively charged and neutrally charged particle that are clumped together in the middle of our atom in the nucleus right here. And then this negatively charged atom that's going around the outside. So just as a quick little mini pop quiz right here, feel free to answer either out loud or in the chat. What are these particles right here? These positive particles that are in the middle of the atom, what are these guys called?
Protons.
Protons, bingo. So in this picture of helium, we have 2 protons right here, 2 positive charges. So protons hang out in the middle. And there's another type of particle there too. These guys that don't have any charge, these kind of gray looking guys right here. What are these particles called?
Neutrons.
Neutrons. Exactly. Neutrons are here in the middle with the protons. So our positive protons and our neutral neutrons are hanging out in the middle part of our atom right here. And then what are these negative particles that are on these rings around the outside?
Electrons.
Electrons, bingo. So these guys are our electrons. Electrons are negatively charged particles, and they do not go in the middle of the atom like we talked about on Tuesday. They go around the outside of the atom, and electron shells are what we refer to them as. So as we talked about, last week and this week, you can figure out how many electrons that you have in your atom by looking at the atomic number, which is also the same as the number of protons. So like in helium right here, helium has an atomic number of 2. So helium has 2 protons, and more importantly for us these last couple days, 2 electrons. So we know that the electrons don't just randomly circulate around the outside of the atom like we talked about on Thursday. They happen in these electron shells. So the closest shell into the middle is the first shell, and then the one that's a little bit further out from that is the second shell, and the one further out from that is the third shell. So not only do these electron shells determine where the electrons of the atom go, but as you'll see today, they also determine how an atom behaves when it encounters other atoms. Specifically, the electrons on that outer shell, whatever the most outer shell of our atom is, that is going to determine what that atom will do when it comes into contact with other atoms that are around it. So there are certain rules about how electrons are placed in their electron shells. So does anybody remember what's the maximum amount of electrons that can fit on the first shell?
2.
2.
2, exactly. First shell, smallest shell, can only fit 2 electrons on it. What about the second shell? How many can fit on the second shell max?
8.
8. Exactly. 8 max on the second shell. And then what about the third shell? How many max can fit on the third shell?
8.
Exactly. Also 8. Some people got a little bit confused about that on the homework with the oxygen because they were trying to put in just the maximum amount of electrons, which was not correct for that homework. But also, a lot of people thought that the third shell had 18 electrons on it. And if you Google how many electrons are on the third shell, some of the answers will come up on the Google as 18. That's because they're talking about a little bit different way than the electron shells are configured compared to the way we're talking about. They're doing a little bit more in-depth, very chemistry-focused way of looking at it. And we're not quite to that level at this point. So for our purposes, second and third shell can both fit up to 8 electrons. Not 2, not 18, not 10, 8 on the second shell and 8 on the third shell. So first shell gets 2, the other ones get 8. So I mentioned earlier that whatever the outermost shell of the atom is, the electrons on there are going to be really important. And in fact, they are so important that scientists have even given them their own name. And we call those valence electrons. Hey, Vanessa, thanks for being here. So valence electrons are the name given to the electrons on the outermost shell. Some atoms might have 3 valence electrons, some might have 6, some might have 8 valence electrons. Whatever the most outer shell is, the electrons on that shell are called valence electrons. We'll talk about in a little bit exactly why they are important. But they are important, and because they're so important, they get their own fancy name. So for some atoms, that outer shell might be the second shell. For some atoms, that outer shell might be the third shell. For a couple atoms, the really, really small ones, hydrogen and helium, their valence electrons are on their first shell because they're so small they don't even have a second or third one. But whatever the outer shell is, those are our valence electrons. So it works kind of like this. Here we have some atoms with a nucleus and some electron shells going around it. I mentioned that hydrogen's kind of funny. He's so tiny. He only has one valence electron on its first shell. So the way that these shells work, they have circles on them for the maximum amount of electrons that can go there. And then the filled in circles are how many electrons are actually there. And the open circles are spaces that were not filled up by electrons. So like with carbon over here, carbon has 6 total electrons, right? Atomic number is 6, which means protons is 6 and electrons is 6. So we put 2 electrons on the first shell, but then the first shell is full. So we have 4 more left over that go on the second shell. So carbon has 4 valence electrons, 4 electrons on the most outer shell, which for carbon is the second shell. Nitrogen has 1 more electron, so it has an atomic number of 7. So nitrogen has 7 electrons. 2 go on the first shell, and then the remaining 5 go on the second shell. So nitrogen has 5 valence electrons, and then since it doesn't have 8, it still has space for 3 more if it needed to have them. And then oxygen, like you may recognize, has an atomic number of 8. So oxygen has 8 protons and 8 electrons. So oxygen has 2 electrons on the first shell, and the remaining 6 go on the second shell. So oxygen has 6 valence electrons, 6 electrons on that outer shell. So carbon, 4 valence electrons, nitrogen, 1, 2, 3, 4, 5 valence electrons, and oxygen, 1, 2, 3, 4, 5, 6 valence electrons. So the reason that it's important to know how many valence electrons an atom has is due to something called the Octet Rule. So oct is like 8, as in octagon, the shape that has 8 sides, or octopus, the animal that lives in the sea with the 8 arms. And when scientists were first studying atoms and how they interacted with other atoms, they realized that atoms really, really want to have 8 electrons in their outer shell. I mean, except hydrogen and helium, they have an outer shell of the first shell, so they only want 2. But all other 100-something other atoms on the periodic table, they want 8 electrons on their outer shell. So the octet rule says we really, really want 8 electrons. So atoms will do a whole bunch of different stuff in order to make it so that they have 8 electrons on the outer shell. So some atoms will gain electrons. They'll take electrons from other atoms to make it that way. Some atoms will lose electrons. They'll give away electrons in order to get down to 8. And some atoms will share their electrons. So they'll share electrons with other atoms so that they can feel like they have 8 in that outer shell. So, for example, carbon has 4 out of the 8 valence shell electrons. So the octet rule says that carbon would like to gain 4 more electrons. So carbon has 4 electrons already in its outer shell. So if carbon could add 4 more electrons on there, it'll be a happy little atom. So carbon is trying to get 4 more electrons. Nitrogen has 5 outer shell electrons, which means it has space for 3 more electrons. So nitrogen wants to gain or share electrons so that it can get 3 more electrons added to its outer shell. And then finally, oxygen, with its 6 out of 8 valence electrons, wants 2 more electrons in order to make it that full 8. So the octet rule says that atoms will try to make it so that their outer shell has 8 electrons. Whatever they have to do, whatever borrowing or sharing or taking or giving, whatever they need to do, they want an 8 electron outer shell. So that is why these valence electrons, these outer shell electrons, are so important. They determine what types of connections that one atom will make with another. All right, so I know that's a whole lot of information about valence electrons and octet rule stuff so far. Does anybody have any questions, anything about electron shells or the octet rule that you're still a little bit confused about, still a little lost on?
No.
All right. So remember, valence electrons are the ones on the outside. And the octet rule says that we're always trying to get to 8. We always want to have 8 electrons in that outer shell. So again, depending on the atom that you're dealing with, you may be dealing with a different outer shell. So like here's the 3 that we were just looking at: carbon, nitrogen, and oxygen. And obviously other atoms have different numbers on the second shell. So like boron over here only has 3 electrons on its second shell. Fluorine over here has 7 electrons on its outer shell, so it's really close. And then neon, like we mentioned on Thursday when we went over the shells, neon has a full outer electron shell. So neon doesn't want to share or take or give away any electrons. He is all set with his electrons. So one of the cool things about the periodic table, and the reason it's set up in the way that it is that for the most part, the families, meaning these columns here, the vertical groups of atoms, usually have the same number of valence electrons. So for example, we already mentioned that carbon has 4 valence electrons on its second shell. Silicon on the next level down also has 4 valence electrons. It's just that silicon has them on the third shell. So silicon has 14 electrons. No worries, Robert. Thanks for being here. Silicon has 14 electrons, so he's able to fill up his first and second shell and then have 4 electrons on the third shell. So silicon and carbon both have 4 valence electrons. Same thing with nitrogen and phosphorus. These guys both have 5 valence electrons. Nitrogen has 5 on the first shell, or on the second shell. Phosphorus has 5 on the third shell. Same thing with oxygen and sulfur. Oxygen 6 on the second shell, sulfur 6 on the third shell, and so on and so forth for all of these columns on the periodic table. So again, argon down here also has a set of 8 electrons on its third shell. So if you remember on Thursday last week, I mentioned that neon and argon belong to that group called the noble gases because they already have a full outer shell. They already satisfy the octet rule. So they do not want and do not need to be messing around with any of the electrons from any of these other atoms over here. They just want to go off and be on their own and not mix and not react with any of these guys over here. They already have that octet rule all set. Thank you very much. So no matter if it's the second shell or if it's the third shell, the valence electrons are the ones on the outside, and the number of valence electrons determines how many electrons an atom will give away or take or share in order to make it to that octet rule, in order to get to that 8 valence electron number. So because these valence electrons are so important, sometimes scientists don't even bother writing in all the other electrons that are underneath them. So sometimes you'll see valence electrons represented with what are called electron dot structures. Basically, it's just a way of having the symbol of the atom represent all of the first shell or first and second shell electrons. And then the dots surrounding the symbol represent the valence electrons. So like carbon over here has 4 valence electrons. So there's 1, 2, 3, 4 dots around carbon. Nitrogen and phosphorus both have 5. 1, 2, 3, 4, 5. Oxygen and silicon both have 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and so on and so forth. So I don't use these a whole ton, but I do bring them up just in case you see them at some point down the line and you're kind of confused about what all these dots are doing. They're just showing you the valence shell electrons, the electrons that are on that outermost electron shell. So to bring this back to chemical bonds, that thing at the very beginning I said we were going to talk about, the reason why atoms bond together and make these chemical bonds is because they're trying to fill those electron shells. So when atoms give or take or share electrons with each other, it causes them to bond together. It causes them to become stuck together, essentially. And that is what causes these new compounds, these new substances to be formed. It's all because we're trying to get to 8 electrons on that outer shell. So overall, there's 3 different types of chemical bonds, but there's 2 that we're really going to focus on today. These first 2 right here. Metallic bonds we'll talk about a little bit, but they're not really as important or as interesting. But the main ones we're going to talk about are ionic bonds, where we transfer electrons from one atom to another. So one atom gives away its electron, and one atom takes the electron. And then the second type are called covalent bonds. And this is when atoms share the electrons between them. So both atoms use the same set of electron pairs in order to bond together. So we'll go ahead and talk about ionic bonds first. And ionic bonds are formed, like I said, when atoms transfer electrons from one to the other. One atom gives away 1 or more electrons, and another atom takes the electrons. So a lot of times you see ionic bonds between metals and nonmetals. You don't have to worry about electronegativity stuff. We're not going to talk that in depth. But metals and nonmetals are what tend to form ionic bonds. And again, it's formed by transferring electrons, physically moving electrons from one atom to another. Don't worry about this third one. We're not really going to go into that. So things like sodium chloride. Sodium is a metal, chlorine is a nonmetal. Same with calcium chloride. Calcium is a metal. Chlorine is a nonmetal. Potassium oxide, potassium, metal, oxygen, nonmetal. So the way that ionic bonds work is something like this. So actually, I'm going to zoom back a little bit. So that one that I was showing you, the sodium chloride, if you look at our little diagrams down here, sodium is way over here. He's got one little valence shell electron. Chlorine, way over here, has 7 valence shell electrons. So sodium just has the one little one. Chlorine has 7. So here we have a sodium and a chlorine. I showed you that picture earlier because I don't have any way of making this little animation pause or stop. And so it's just going to be going the whole time. So this little yellow dot is the valence electron on sodium. And the 7 red dots are the valence electrons on chlorine. So sodium has 1 valence electron on his third shell, which means that if he could somehow give away that electron, he would no longer have a third shell, and instead he'd move down to his second shell, which already has a full set of 8 electrons. So if sodium can give away that 1 third shell electron, he can satisfy the octet rule by having 8 second shell electrons be his outer shell. So he's trying to get rid of that 1 single pesky electron that's hanging around. Chlorine has an almost full third shell. Chlorine's got those 7 valence electrons. So if chlorine could just take or grab 1 more electron from a substance, from another atom, then he could have a nice, full, complete set of 8 valence electrons satisfying his octet rule. So sodium is trying to give away that electron. Chlorine really, really wants to take an electron, so it's a match made in heaven. Sodium transfers that electron to chlorine. So now sodium no longer has a third shell. He just has a full second shell. And chlorine is able to take that little electron from sodium and give himself a full third outer shell of 8 electrons. So now they are both happy. They're both able to satisfy that octet rule. So sodium gives away his electron and chlorine takes it. So now we have a full second shell on sodium and a full third shell on chlorine. 2 happy little atoms. But what is it that's actually bonding these atoms together? Why does this transfer cause them to bond and stick together? Well, it all has to do with the fact that after this electron gets moved, you might have noticed we get this little plus and this little minus popping up on our atoms. Remember, electrons are negatively charged. So when sodium gives away that electron, when sodium gives away that negative charge, it becomes a little bit more positive. It's gotten rid of some of its negative, so now it's more positive. Chlorine, which has added that electron, is now a little bit more negative than before. It's added that negative electron, so now chlorine is more negative and sodium is more positive. And in science and chemistry and physics, opposites attract. Just like that old romantic saying that you've heard before to explain how 2 different people who seem like they want to be into each other get along really well and maybe end up dating and getting married. Same thing essentially happens with sodium and chlorine right here. The positive and the negative on these 2 different atoms cause them to be attracted together. It's almost like a magnet, if you want to think about it that way. Sodium is positive, chlorine is negative, and when you put positive and negative close to each other, they are attracted to each other. They want to stick together. And that is what creates our ionic bond. We transfer this electron away. The sodium becomes more positive, the chlorine becomes more negative, and then these guys bond together. That positive and negative are attracted to each other and causes sodium and chlorine to bond together to become a new substance, a new particle, sodium chloride. So now this Na and this Cl are stuck together. They have formed one new compound, sodium chloride. Right, so remember from Tuesday, compounds are what we get when different atoms get stuck together or bond together. So sodium chloride is our new compound. It is our new substance that is different from sodium on its own and chlorine on its own. So this is a very classic chemical reaction or chemical change, right? We start off with sodium and chlorine atoms, but then we end up with the compound sodium chloride. It's a different substance, a new substance that's been produced that has new different properties. So we move this electron over, sodium becomes positive, chlorine becomes negative, and the positive and negative opposites attract to each other, creating a bonded atom or a bonded compound, sodium chloride. So ionic bonds, all about transferring that electron. One gives it away, one takes it, they become oppositely charged, and that bonds them together. All right, any questions so far? Anything about ionic bonds and transferring electrons that still isn't very clear, that you're still a little confused on?
So when the sodium ion, or if with any of them that give away the electron, they become positive because they gave it away?
Exactly.
Okay.
So before they were totally balanced, right? So we have our protons that are in the middle here that are positive, and the electrons that are negative, and they're nice and balanced with each other at first. But when sodium gives away this negative electron, now it's got a little bit more protons than electrons. So now it's got a little bit more positive than negative. And then the opposite happens with chlorine. Chlorine takes that electron, it takes on that extra negative charge, and so that makes chlorine a little bit more negative. All right, great question. Anybody else have any ionic bond question, any positive, negative questions about this process? All right, so you may remember from the other day, we mentioned sodium chloride briefly, actually, when we were talking about compounds. Because sodium chloride is table salt. So if you get a whole bunch of sodium chloride atoms that all get structured together into a big crystalline solid, it forms the solid that we know as table salt, the tasty stuff that you sprinkle on your food to give it a little bit extra flavoring. So again, two very different atoms that then bond together by transferring that electron, and we can stack a whole bunch of them together and make salt. So that is ionic bonding. One atom gives away some of its electrons, the other atom takes the electrons, and that difference between the positive and the negative cause them to become bonded, cause them to become stuck to each other. The next type that we're going to mainly focus on, covalent bonding, has the same end result, two or more atoms stuck together, but it goes about it in a little bit different way. In a covalent bond, we share the electrons. So there's no giving and taking of electrons, but instead the atoms share pairs of electrons with each other. So again, there's some stuff here that you don't really have to know about, but covalent bonds tend to happen between nonmetals. So like oxygen, like I mentioned the other day, likes to bond with itself a lot, and oxygen is a nonmetal. Carbon dioxide, I mentioned when we talked about compounds on Tuesday. Carbon and oxygen are both nonmetals. Same with C2H6, which I believe is butane, if I remember my organic chemistry correctly. Carbon and hydrogen, both nonmetals. H2O, our good friend water, is the result of a covalent bond between two hydrogen and one oxygen. And then even silicon chloride, not chloride, silicon carbon is also a covalent bond. Again, silicon, nonmetal, carbon, nonmetal. Actually, silicon is a metalloid, but it's close enough to a nonmetal in this case that they can still make covalent bonds. And again, it's all about sharing electrons, both atoms getting the same use out of the same set of electrons. So the way that covalent bonds work and the way that they look is something kind of like this. So here we have the compound CH4, 1 carbon and 4 hydrogen atoms that are all bonded together and sharing their electrons. So the blue dots on here represent electrons from carbon. And carbon has 4 valence shell electrons, if you remember correctly. Carbon has an atomic number of 6 electrons, 2 on the first shell and 4 on the outer second shell. Hydrogen, if you remember, just has the 1 lone electron on his outer shell. So carbon, again, it has 4. It's trying to get 4 more electrons so it can get to 8. Hydrogen is the little guy, so he only wants 1 more electron, so he can get up to 2 and have a full first shell. So carbon and hydrogen first meet each other, and when they covalently bond, hydrogen shares its atom with carbon, and carbon shares its atom with an electron, with hydrogen. So now this hydrogen is happy because he feels like he has 2 outer shell electrons, 1 of his own, and then 1 that he's sharing with carbon. So these electrons count both towards hydrogen's octet rule and carbon's octet rule. Same thing with this hydrogen and carbon up here. Again, hydrogen shares his 1 electron, carbon shares 1 of its valence electrons. So now this hydrogen feels like he has 2. This hydrogen shares his electron and carbon shares back. So now he feels like this hydrogen has 2. And same thing down here. So each one of these hydrogens is happy because based on the sharing, each one feels like it has 2 first shell electrons, which makes it full. And this carbon is happy because thanks to all the electrons that the hydrogens are sharing, carbon now feels like it has 1, 2, 3, 4, 5, 6, 7, 8 outer shell electrons for carbon. So again, we are sharing the electrons. Both of these electrons count for this carbon and for this hydrogen. And so because we're sharing the electrons, it causes these atoms to become physically bonded together. Their electron shells essentially overlap and stick together. So unlike with the ionic bond, where we had the positive and negative that were attracted to each other, in this one, they are physically stuck together by sharing these electrons. Again, here we have 2 atoms that have 7 outer shell electrons. So this could be like fluorine, for example. It's a couple steps up from chlorine or from carbon. Carbon has 4 outer shell electrons. Fluorine has 7 outer shell electrons. So when 2 fluorine atoms come into contact, the right one has his 1 electron that he then shares with the other one, and the left one shares its electron back. So now these guys are sharing 2 electrons with each other. And so each one feels like it has 8 outer shell electrons. The 7 that it started with, plus the 1 that it's sharing, that the second atom is sharing with it. So they become stuck together because they're sharing that electron. So now each one of these guys feels like it has its original set of 7 plus the 1 more from the second atom to give it 8. That is what making a covalent bond is all about. Again, covalent because we are co-sharing our valence electrons. So usually this happens in pairs where we have a certain number of electrons and then we share 1 or 2 with another atom so that everyone feels like they have 8. We become physically stuck together by sharing that outer shell electron. So whenever you think about ionic bonds, I want you to think about transferring electrons, giving away and taking. When you think about covalent bonds, I want you to think about sharing. Both atoms using a shared set of electrons in order to get both of them up to that 8 level. Or in the case of hydrogen, getting up to that 2 level. But sharing is what these covalent bonds are all about. So a little bit more straightforward than the ionic ones because we don't have this transfer and this positive and this negative. They literally just come together and then mix their electrons, share them with each other so that they can get that full outer shell. All right, does anybody have any covalent bond questions? Anything about the covalent bonds that you're still a little confused or still a little unclear about?
No. No.
All right, cool. So the last one that I'm going to go through really quick, we're not really going to focus on it in this class, but it is out there. It's called a metallic bond, and as you might expect, it tends to happen between metals. So like when you get a lot of sodium or iron or like aluminum, like if you think of the sheet of aluminum foil at your house, all those atoms in that solid aluminum are probably connected with metallic bonds. And those are what help metals become very good conductors, like we talked about the other week, where essentially all of the electrons are like constantly being shared with all the other atoms around it. So instead of having these like super defined electron shells and the sharing or the transferring, all the electrons are kind of being shared all at once with all the other atoms. So they all feel like they have a full outer shell, even if it's just electrons that are constantly moving all around them. So again, we're not really going to focus on metals too much here. And so metallic bonds are out there. It is what tends to connect metals together. But again, we're not really going to focus on it in this class. The main ones to look at are those covalent and ionic bonds. So since you guys are still working on that midterm, which is due by the end of the day tomorrow, I made it a pretty simple, straightforward assignment to go over chemical bonds for your homework or daily assignment for today. So I made these two diagrams. There's this one between lithium and fluorine up here. And there's this one between hydrogen and fluorine down here. And so for each one of these diagrams, I want you guys to tell me what type of bond is being pictured in these pictures. Is it an ionic bond or a covalent bond? And then second, how can you tell? What is it about this diagram? What is it about this picture that tells you that this is definitely an ionic bond? Or that tells you that this for sure is a covalent bond? So just 4 questions, should be pretty simple. What kind of bond is it? And how can you tell? What makes it an ionic bond versus what makes it a covalent bond? So that is the homework assignment for today. Again, pretty short and simple because you do still have the midterm going on. So remember, the midterm is not due until the end of the day tomorrow. So you have the rest of the evening tonight and all day tomorrow to work on it. It is a little bit long, so don't think that you can sit down at like 11:45 p.m. tomorrow night and pound it out real fast. I would definitely recommend taking a little bit more time on it than that. Read the questions, make sure you understand what they're asking about. You can always reach out to me if you need a little bit of help. I obviously cannot help you directly answer the question, but I can help you figure out what the question is asking and what kind of answer that it is looking for. So again, the midterm covers everything we've talked about so far, including the mixtures and compound stuff from Tuesday and potentially some chemical bonding stuff from today. So take your time on it. You still have plenty of time to work on it, but do please make sure that you get it turned in by the end of the day on Friday. And then like I was saying earlier, make sure to check back in on Monday for a quick little daily question about valence electrons and the octet rule. So night school still has class on Monday, so make sure you come back and check in and do that daily assignment in order to get your attendance counted for Monday, May 3rd. All right, does anybody have any final questions about the notes from today or the homework assignment for today or what's going on this week or next week in class?
I have a question about the midterm.
Sure.
Okay, so I did it and I turned it in, but then it's showing again that I didn't turn it in. Can you check for me and see if it went through?
Sure, I can check. Also remember that if you do it on the Google form, then whenever you hit submit on Google form, it unfortunately does not tell the Google Classroom that you did it. So it'll still show up and look like it's missing on the.
Yeah, I usually do like mark as done, but this time it didn't do it for me. So that's why I was wondering what was going on.
Interesting. Yep, I can definitely look into it and let you know if I got a copy of it. If I don't get back to you sometime tonight, then just send me an email or a text tomorrow to remind me, and I can look into it pretty quick.
Okay, I'll do that because I just want to make sure it did go through, or else I can go ahead and do it again.
Yeah, no, the midterm is worth a big chunk of your overall grade. So yeah, definitely a good idea to double check and make sure that it went through. Always a good thing to do and something that I can check pretty quick.
Okay. All right, thank you.
Yep, no problem. All right, any other compound or bonding or midterm related questions?